More than 30 times farther from the Sun, almost at the edge of our solar system, lies the mysterious planet Neptune. It's impossible to see it even from the highest points on Earth without a telescope due to its remoteness. Neptune is the least explored planet in our entire system. But what could be so mysterious about this planet? Would you be surprised if we told you that Neptune, one of the coldest planets in the system, can support an ocean of superhot water? Today, you'll learn about that, as well as Neptune's strange rings, what makes it so blue, and also what is now known about its famous satellite, Triton. Neptune is an ice giant about 4 times wider than Earth. It has a radius of about 1,500 miles and a volume of 15 trillion cubic miles, which means that Neptune is 58 times larger than Earth in volume. The planet is composed mostly of water, methane, and ammonia. Like the other ice and gas giants in our system, Neptune has no solid surface. Its atmosphere extends deep into the planet to the mantle, which is composed of methane and ammonia ice and a rocky core. Nevertheless, scientists believe that the ice giant could theoretically have an internal hot ocean. But how can a planet sustain such an ocean since it's so far from the Sun? It would take sunlight 4 hours to reach the giant's surface. Neptune's average atmospheric temperature is -360 degrees Fahrenheit, making it one of the coldest objects in the solar system. In addition, according to recent research, most of Neptune cooled from 2003 to 2018, despite warming near the South Pole from 2018 to 2020, likely due to seasonal changes in atmospheric chemistry. The reason for the likely formation of the ocean inside the ice giant remains unsolved. However, scientists suggest that this strangeness can be explained by internal heating released due to gravitational compression or gravitational interaction between Neptune and one of its satellites, Triton. On the other hand, researchers Sloan Viktorovich and Andrew Ingersoll believe that the probability of oceans on Neptune due to its heat is very low, only 15% at this time. According to science's calculation, only in 1 billion years, with a chance of an ocean, they're increased to 40% after the giant cools down. Another explanation for the huge internal energy could be Neptune's collision with some cosmic object, because Neptune is the only planet that emits nearly 3 times as much energy as it receives from the Sun. This is also confirmed by the unusual 28-degree tilt axis, almost as much as on Earth. Because of this, Neptune also experiences seasons similar to ours. Neptune, the 8th and farthest planet from the Sun in our solar system, remains one of the most enigmatic celestial bodies. Its remoteness, situated more than 30 times farther from the Sun than Earth, renders it invisible to the naked eye, necessitating telescopic observation even from the highest vantage points on our planet. Despite being one of the least explored planets in our solar system, Neptune harbors a plethora of mysteries waiting to be unraveled. One of the most intriguing aspects of Neptune lies in its capacity to host an ocean of superheated water, a remarkable phenomenon considering it ranks among the coldest planets in the solar system. With each season on Neptune spanning approximately 40 Earth years, and a Neptunian year lasting a staggering 165 Earth years, the planet's rotation is notably swift, completing a day in a mere 16 hours. This rapid rotation generates immensely powerful winds, a feature we'll delve into shortly. Neptune's atmosphere, predominantly composed of hydrogen, 80%, helium, 19%, and trace amounts of other gases, including methane, holds the key to its distinct azure hue. Methane clouds in the upper atmospheric layers absorb solar shortwave radiation, reflecting the characteristic blue coloration. Interestingly, its neighboring planet, Uranus, boasts a similar gas composition but exhibits a pale blue tint. Dr. Patrick Irwin of Oxford University postulates that this disparity in coloration could stem from variations in methane fog density, resulting in divergent aerosol layers within their atmospheres. Delving deeper into Neptune's atmospheric structure reveals a complex stratification comprising several layers of aerosols. The deepest layer comprises a mixture of hydrogen sulfide ice, lending certain regions, particularly those near the poles, a darker appearance. Above this lies a haze particle layer where methane ice forms and precipitates as methane snow. Due to Neptune's heightened atmospheric activity compared to Uranus, it efficiently produces this snow, resulting in a thinner second aerosol layer, thereby intensifying the planet's rich blue hue. Continuing upward, the third atmospheric layer also consists of large methane ice particles, effectively extending from the second layer. Aside from its captivating azure hue, Neptune's surface is adorned with dark and white patches, which are manifestations of the planet's rapid axial rotation. Clocking wind speeds of up to 2,200 miles per hour, Neptune reigns as the windiest planet in the solar system, boasting winds nearly 4 times stronger than those on Jupiter. Among its notable atmospheric phenomena is a colossal storm known as the Big Dark Spot, akin to Jupiter's famed cyclones. Initially detected by the Voyager 2 spacecraft in 1989, this cyclone-like vortex orbits Neptune at speeds reaching 1,500 miles per hour. However, unlike Jupiter's enduring cyclonic systems, Neptune's large-scale vortices have fleeting lifespans, typically persisting for only 2 to 6 years. Further complicating Neptune's atmospheric dynamics are the intermittent formation and dissipation of these storms, presenting a puzzling conundrum for scientists. Recent observations in 2018 revealed a new storm emerging, drifting southward before abruptly reversing course, a phenomenon hitherto unseen. Such atmospheric disturbances offer valuable insights into the intricate processes governing Neptune's weather patterns, shedding light on the formation of enigmatic features across the planet's surface. Beyond its atmospheric mysteries, Neptune also boasts a ring system, a characteristic shared with other gas giants in our solar system. In 2022, the James Webb Space Telescope captured a near-infrared image unveiling Neptune's ethereal rings and orbiting satellites, marking a significant milestone in our understanding of the planet's celestial dynamics. This groundbreaking observation marks a pivotal advancement since Voyager 2's last image more than 3 decades prior. Neptune's profound enigmas continue to captivate astronomers and researchers alike, beckoning further exploration and scientific inquiry. With each revelation, we inch closer toward unraveling the secrets shrouding this distant ice giant, illuminating our understanding of the dynamic processes shaping our solar system's outermost realms. In the recently captured photograph by Webb, we can discern approximately 5 distinct rings encircling Neptune. Each of these rings is named after astronomers who made significant contributions to our understanding of Neptune and its surrounding environment. The first ring, named Hale, is the closest to Neptune and exhibits a remarkable diffuseness, spanning approximately 26,000 miles in diameter, with a radial width of 1240 miles. Hale is comprised of a substantial amount of dust, ranging from 40 to 70%. This significant dust content contributes to its diffuse appearance and distinguishes it from the other rings. Moving outward, we encounter the second ring, Leverrier. Although Leverrier appears brighter in comparison to Hale, there exists some uncertainty in its measurement, resulting in a margin of error. Nevertheless, Leverrier spans a width slightly exceeding 62 miles, indicating its prominence in Neptune's ring system. The next ring, known as Lasso, boasts the title of being the widest among all of Neptune's rings, stretching approximately 2,485 miles across. Interestingly, Lasso exhibits a relatively low percentage of dust, ranging from 20 to 40%. Despite this lower dust content, Lasso's expansive width contributes significantly to its presence within Neptune's ring system. Moving further outward, we encounter the fourth ring, Arago, which presents some challenges in observation due to its relatively small size. With a radius of 35,540 miles, Arago resides on the outer periphery of the Lasso ring. Its minimal dust content renders it scarcely noticeable, distinguishing it as one of the smallest rings within Neptune's ring system. Finally, we arrive at the last ring, Adams, which features a remarkably narrow width of only 35 kilometers. Despite its slender appearance, Adams possesses an orbital radius of approximately 39,724 miles, positioning it as the outermost ring in Neptune's ring system. However, what truly sets Adams apart are its arcs, bright bands of dust encircling the ring. Each arc bears a distinct name: Freedom, Brotherhood, Courage, and Equality. These arcs exhibit dynamic behavior, with Brotherhood and Equality exchanging material and altering in size. While the exact cause of their formation remains uncertain, researcher Empty de Peter suggests that it could be attributed to the collapse of a parent companion or another celestial object within the Roche limit. In addition to capturing images of the rings, Webb also recorded 7 of Neptune's 14 satellites. These moons, classified into regular and irregular categories, include 6 inner satellites captured in the image. Notably, Triton, the most distant and brightest satellite, stands out in the photo. Triton's luminosity surpasses that of Neptune due to its nearly complete coverage by nitrogen ice, reflecting about 70% of the sunlight that reaches its surface. With a diameter of 1,680 miles, Triton ranks as Neptune's largest satellite, even surpassing Pluto in size, comprising 99.7% of the total mass of all of Neptune's moons. Neptune's moon Triton holds several remarkable distinctions. It stands out as the coldest geologically active object within the solar system, with surface temperatures plummeting to a bone-chilling negative 391 degrees Fahrenheit. This extreme cold is attributed to Triton's icy surface, which reflects light, similar to other moons of ice giants. Despite its frigid temperatures, Triton experiences wave blocking, meaning that only one side perpetually faces the planet. Its retrograde orbit, contrary to the majority of satellites in our solar system, sets it apart. This orbit causes Triton to move in the opposite direction to Neptune, resulting in alternating exposure of its poles and equator to the Sun. Scientists posit that Triton's unusual orbital tilt suggests it didn't originate with Neptune, but was likely captured from the Kuiper Belt by an ice giant. This capture event, coupled with Triton's hypothetical ability to orbit other objects, prevented a collision with Neptune and influenced its orbital characteristics. Triton's surface features, as revealed by images from Voyager 2 in 1989, showcase a mosaic-like appearance with prominent plumes and craters. The age of these surface features ranges from 10 million to 100 million years, indicating significant geological activity. Scientists speculate that Triton may harbor a subsurface ocean, evidenced by plumes and depressions resembling lake basins. Additionally, the presence of ammonia beneath its surface slows water freezing, suggesting the potential for an oceanic world. However, confirming Triton's oceanic nature remains challenging. Moreover, Triton's association with the Kuiper Belt raises questions about Neptune's influence on its celestial objects. The Kuiper Belt, an area beyond Neptune, comprises small and large celestial bodies, including dwarf planets like Pluto. Some objects within the belt, including Pluto, exhibit long-range resonance with Neptune, suggesting gravitational interactions. This resonance suggests that Neptune's migration from the inner solar system likely influenced the retention of Kuiper Belt objects within the system, preserving approximately 70 objects in resonant orbits. Despite Triton's enigmatic nature and Neptune's influence on its surroundings, many mysteries persist. Scientists await future expeditions to unravel Neptune's interior composition and the formation processes of ice giants, shedding light on the complexities of these distant worlds. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.